Hello my student, this clip I'm going to show you how to solve the problem in chapter 4 including finding the mechanical properties of the materials and also using those mechanical properties of material to compute the deformation of a simple structural member ABC here. Okay, they give us a graph of the stress strain diagram here, and this represents the behavior of metallurgical alloy, and the graph have two scales. One is the upper scale, which will cover the whole behavior of this alloy, and another one is for this scale to zoom out this portion of the graph which is too close to the vertical axis. So we cannot compute some important properties of this alloy without doing the second scale. Okay, and the zooming is quite large when you divide 0.04 by 0.005. Okay, and they said this stress strain diagram provide the yielding stress and the proportional limit stress at the same point. Okay, they like us first to find the proportional limit of the material, and then determine the ultimate stress, and then the fractional stress, okay, and modulus of elasticity, and the modulus of resilience of the material. Okay, when you consider stress strain diagram, the first part, if you like to find the proportional limit, what is proportional limit? Proportional limit is the last point. That's the relationship between stress and strain is linear. Okay, so usually if you like to find that, you need to put your graph and then you mark it with the straight line. When the straight line separate, when the graph separate from the straight line, that's point gonna be the proportional limit stress. And by doing this, you may find this point by putting your ruler, okay, in parallel to the vertical axis, and then when you arrive at this point, you may get this one to be this point. Okay, and let me zoom this one a little bit so we can work over it clearly. So what do we have now? You have what? You have this point as your proportional limits, and this point, the stress sigma sub PL is equal to sigma sub Y. How can you determine it? You can relate it directly, okay, by estimating it to be 200 something, that's close to 300. But to be more systematic, you should measure this. Okay, you may see this is going to be about 10 millimeter. So this is going to be 10 millimeter, and then you get the stress of 100 megapascal. Okay, and if you measure this, you may get this one 1 2 3 4 5 6 7 8. Somebody said it's 8.2, somebody said it's maybe 8.1. It's up to your estimation. So the answer to this kind of problem is not exactly. I will get some interval for the solution of the stress. Okay, it's maybe 280 to 285, and if you measure this to be 5 6 7 8, okay, you get this one is 8 millimeter. So this one gonna be 8 times 100, and you divide it by 10. and then you get this for 80 megapascal. Okay, when this is 80 megapascal, that means you measure from this for 80 megapascal. So your sigma sub PL should be 280 megapascal. Okay, you understand that, right? And then they ask us to determine the ultimate stress. To determine ultimate stress, you may need to do something. The ultimate stress has the slope of the curve. It is the highest point of the stress strain diagram. So the slope at the ultimate stress is going to be 0. So when you move your ruler up, reach the point, and you can estimate that you're going to point with the 0 slope, and then you will get this as the sigma sub u. Okay, and again, you do the measurement. This is going to be 100 megapascal, right? And then you measure this 1, 2, 3, 4, and you get this 5. Okay, if this 5 from your proportion, that's going to be over here going to be 50. So it's going to be 500 plus 50. So your sigma sub u can be 550 megapascal for this. Okay, and next they ask us to find the fracture stress. This is the point of fracture stress. Okay, the stress corresponding to this point is going to be sigma sub f, and it's just above the 400 line, just above 400 line. So if you be very careful on this, okay, you may project like this, or you may answer this for 400, or if you can estimate this, you can answer this for 405 megapascal. So sigma sub f may be 405 megapascal. Okay, and next they ask us to determine the modulus of elasticity. Okay, the modulus of elasticity is follow the Hooke's law, sigma equal to E times 10. It can compute for the linear elastic region, so it only can compute up to the proportional limit, or practically it's up to the yielding stress. So the E is going to equal to sigma divided by strain. Okay, and then if you use this sigma proportion to be the last point, and then you project down here. Okay, so the corresponding strain going to be 0.001. Since this one is corresponding to 0.01, so this one going to be sigma sub what? Sigma sub, this is sigma sub PL, and the strain here is going to be strain sub PL, and then you may get this one to be 280 and divided by 0.001. Okay, and then you may get this to be 280 gigapascal. Okay, this is going to be 280 gigapascal. This may be 405 if you like, and you may put the other sigma sub PL to be 280 megapascal and sigma sub U of 550 megapascal. And they also asking you for the modulus of resilience. The modulus of resilience is what? The modulus of resilience is the area. Okay, the area under the stress strain diagram during the proportional limit region. Okay, is the energy that the material can absorb during the linear elastic behavior. Okay, and you also can determine by U sub R equal to 1/2. This is proportional stress, sigma sub PL, and this is going to be proportional strain. And if you put everything together, this is going to be 1/2 of 280 megapascal and times 0.0001 and then meter per meter. The same thing as millimeter per millimeter. You can change it. Okay. And then you will get this one for equal to, this is 140. 140 times 0.001, that is going to be 0.140. And this is mega Newton per square meter, that is megapascal, and time meter by meter. Okay, and you may notice that the unit of force time the length is the joule. So you get this one to be equal to 0.140 megajoule per cubic meter. Okay, that is going to be the ability of this alloy to absorb the energy during the linear elastic behavior. That is the end of the first part to determine the mechanical property of the materials. And the second part, they ask us to determine the deformation of the structure shown here. Okay, and they says this alloy is used to build an axially compressive member ABC, and it says member AB here have 1,500 millimeter length. So if you measure this and this, what you get, this one going to be 1,500 square meter, and the area A sub AB equal to 100 millimeter square. And for the BC, it says BC is here, is have the length of 1,000 millimeter, and the A sub BC 50 square millimeter, and it said the compressive load that acts on this axially compressive member, the P1 is 20 kilonewton. So this one, the P1 is going to be 20 kilonewton. Okay, and you also may see that the P2 is 10 kilonewton. So this is going to be 10 kilonewton. Okay, so from this, they ask us to use the Metrian property that we compute for this stress strain diagram to determine the first one, axial stress in member AB and in member BC. To determine axial stress, you may recall that we have sigma equal to force divided by the area. This is the internal force divided area. So we need to draw the free body diagram of this structure. So let us take this is the reference line of our structure, and you also have this is the C and this is the B. If you consider the whole structure, this is gonna be the AB. Okay, and you also have this for the BC, and it's subjected to the force and is axially compressive force. So it's going to be along this line that's passing to the centroid of the section, and this one is 10 kilonewton. This is 20 kilonewton. If you like, you may say this is X, this is Y, and this is gonna be A sub Y, and since it's the body, so this is supposed to have this one as A sub X, and this one gonna be M sub A. Okay, and then you may use the equation of equilibrium to check, okay, the equilibrium of this. So by using the summation of moment about A equal to 0, passing this point of the centroid, so you get what? M sub A, which is, this is positive, gonna be 0. And the same thing, if you do summation of f sub x equal to 0, so giving this one is positive, so A sub x also 0. So only one that we have is summation of f sub y equal to 0. Upward is positive, so we have A sub y equal to 20, 10 plus 20, that is going to be equal to 30 kilonewton. So that is the reaction, and I'm showing you here that due to the axially compressive load that's passing to the centroid of this member ABC, the moment and the A sub x, they must be 0. Okay, and then since this F is the internal forces, so we need to cut this one for this member BC, and cut this one for the member AB. Okay, if that's the case, we have, oops, only this, not that, only this. Okay, that's for the BC, and for this one, that's for the AB. So they are different. This one we cut only in the portion of the member BC. Okay, and this one will subjected to the force here, and going to have the internal force here. This is subjected to 10 kilonewton. The internal force here gonna be F sub BC. Okay, and for the other one, this is C, this is B, so this one gonna be the force of 10 kilonewton, and this is 20 kilonewton, and the internal force here gonna be F sub AB. Okay, and then you can determine this easily. Summation of F sub y equal to 0, up is plus, so you get F sub BC equal to 10 kilonewton upward. And again, you do this for summation of F sub y equal to 0, up is positive, so F sub AB equal to 10 plus 20, so you get this of 30 kilonewton. And now you can use this internal force to determine the axial stress in this member. Okay, so what we have is the portion BC is here, AB, so we start with the stress for the portion sigma sub AB. So we have sigma sub AB equal to F sub AB divided by A sub AB. And what we have is F sub AB is 30 kilonewton, so it's going to be 30,000 Newton, and then divided by the area of 100 square millimeter. And I like you to observe that if we have megapascal, that is going to be 10 power 6 meter square. No, sorry, Newton per meter square. Okay, and you also know that the meter square is going to be 10 power 6 millimeter square. So the megapascal can be rewritten into Newton per square meter. If you understand that, you may get this one. If you put into your calculator, cut, this is going to be 300 Newton per square millimeter. So the answer here is going to be 300 megapascal. Okay, and next you have sigma sub BC is going to be F sub BC divided by A sub BC. What you have is, this is 10 kilonewton, that is 10,000 Newton, and then divided area here is 50 square millimeter, so it's cut. You're going to have 1,000 divided by 5, so this is gonna be 200 Newton per square millimeter, or you get this one for 200 megapascal. Okay, you can classify the behavior of the material based on comparison the stress with the yielding. If the stress is 200, it's going to be in this region. So this one less than sigma sub y, the behavior of this is going to be in elastic region. Okay, it's 200 megapascal, still here, and since it's in elastic region, we can use the Hooke's law for this. So sigma equal to E times 10. Okay, and if you like to determine the axial strain for this, so the E for this one, the E sub what? E sub strain of BC, will equal to strain, stress of BC, and divided by this one down, divided by the E. Okay, that is going to determine the strain for this portion BC. Okay, if you do that, the strain of this is going to be equal to, this is 200 megapascal, and that is going to be 200 megapascal, and divided by E. If you may recall, E is 280 gigapascal, so it's going to be 280 10 power 3 megapascal. Okay, if you do your calculation, you may get strain of this BC equal to what? 200 divided by 280,000, that is going to be equal to 0.000 and 714. Okay, due to the linear behavior for this member BC. Okay, we got the stress of 200 megapascal, we got the strain of this, and then we have the portion AB. the portion AB have the stress of 300 megapascal. This portion AB, and what is larger than sigma sub y, and this behavior is going to be the plastic. If the behavior of this is the plastic, what we have is epsilon sub AB must be determined from stress strain diagram. Okay, we cannot fight from the Hooke's law. This is, we follow the Hooke's law. Okay, it cannot determine from the Hooke's law. This must be determined from the graph. Okay, if we like to find from the graph, we come here, and 300 megapascal is here. So you got to draw this, and then you can find that it's going to hit this point, and you back down here. And then what you do from the graph is you do the same thing. What is going to be this is going to be the total of 8 millimeter. Okay, 8 millimeter. And then you get this about half of that. Okay, so since this point is a half of 0.002, and this is going to be 0.0025, that's going to be half of that. So the value of this is going to be 0.0002 plus 0.0025 and divided by 2. You may get this to be 0.00225 for this point, half of that. Okay, estimate of that. And then what we get, this one is going to be 0.0025 millimeter by millimeter. Okay. Okay, and let me zoom it out a little bit because we're going to find the third one. Next, they ask us to determine the total contraction of the column. That means what? That means under the stress of 300 and 200, this column may shorten to some distance of this. Let's say this is L palm. So they ask us to determine this, the total contraction. Let me call this one delta of this point C with respect to A, delta C dash A. Okay, and delta C dash A there, delta C dash A gonna include this shortening of the CB and shortening of the AB, so it's gonna equal to delta C slash B, and then plus delta B slash A, that is for the column segment, for the segment AB, and another one that's for the segment BC. Okay, and what we have the equation of the strain. If you may recall, we have the strain equal to delta over L. So the deformation gonna find from the strain times the L. So this one we will have this for the BC, strain BC time L sub BC, and then you're gonna plus strain of this portion AB, and time L sub AB if you like. Okay, this is for the orange and this is for the yellow. Now you have this for equal to strain of the BC is this 0.000714 and the BC is 1000 millimeter times 1000. And you have for the AB plus 0.0025 and this is 1500 millimeter. Okay, if you put them together, the answer gonna be equal to, you pause the clips, put it in your calculator, you can get this for 4.09. And if you like to determine the L palm, you can find the L palm equal to 1000. Okay, and then this one plus 1500, and you got to minus this because this is the shortening of the column, so minus 4.09, and then you may get the L palm of 2495. This is gonna be equal to 2495.91 millimeter. This length now is equal to 2495.91 millimeter from 2500 millimeter. Okay, then they ask us another one. Let me move this one a bit more. Okay, and they ask us what's the total length of the column after we take the P1 and P2 out. That means it's going to recover fully. It's going to recover fully if both of them have the elastic behavior. Since the BC only has elastic behavior and the AB have the plastic behavior, this one gonna recover back. This one gonna have some recover and some for the permanent set. Okay, and if you understand that, your column will have this length. Okay, this length. Let us call it L pum pum. Okay, L pum pum. And by doing that, since this portion, since segment AB has plastic behavior, okay, we have recovery strength and permanent set. Okay, by doing this, the recovery strength, okay, they gonna co-recover in according to the slope of the first portion of the graph. So when this AB have the plastic behavior, and then when the load release, it will not go by this direction, it's only go by this direction with this parallel. So it's recovered by linear elastic, it won't recover by this. So we have some for recovery strength. This is going to be strain recovery, and let's say this one is strain recovery, and this other portion gonna be the strain permanent set. This is gonna be strain PER. Okay, this is gonna be strain PER. So if we like to find the strain PR, we got to use this 0.00225 and minus strain recovery. Okay, by doing this, so we have strain PER equal to 0.00225 and then minus strain recover minus strain REC. Okay, this is going to be strain REC, and we're going to determine what is the strain REC. Since this one follow with linear elastic, so sigma equal to E strain. So strain recovery will be this strain, this stress, the stress divided by E, and the stress going to be stress sub AB. This is the stress of this AB. Okay, so you put that's going to be equal to 300 megapascal, and then you may divide it by modulus of elasticity of 280 10 power 3 megapascal. So the strain recovery here, you can compute it. It can be 0.00107. This one 0.00107 millimeter by millimeter. So coming into this, we have this one equal to 0.00225 minus this one 0.00107, and then we get this permanent strain of 0.00118 millimeter per millimeter. And then now we can determine the permanent deformation delta per from this equation. Delta per equal to strain per time L, and this one is for the AB, so L sub AB, and then we have this equal to 0.00118 and time 1500, and then you get this one equal to 1.77 millimeter. Okay, and now L pam is here, right here. It is going to be equal to 1000 plus 1500. Sorry, 1500, and it's going to be what minus, like it's going to be minus 1.77, and finally you get this one for 2498.23 millimeter. So this is going to be the final length of this one, 2498.23. So the total is 2500. Under apply the force is 2495.91, and then when release the force is going back to 2498.23 millimeter. Okay, that is going to be the demonstration of showing the example for the chapter 4. We start by determining the mechanical property of the metallurgical alloy, and then we use that mechanical property to determine the deformation of this axially compressive member ABC. Okay, that is going to be the end of this clips.